Okay, so now let's talk about the second topic. The second topic is Laplace transform and series solutions. Again, for this topic, we also try to find the solutions of the differential equation. And how do we find the differential equation? Laplace transform is another way to do that. Okay, so what is transform? Transform means I convert an object from one form to another form. For example, like changing variables. When we talk about the Euler differential equation, we let t equals natural log x. So this is Euler differential equation. Remember that why do we use the Euler differential equation? Because later on, we will have a constant coefficient linear differential equation. So this gives us a constant coefficient linear differential equation. It'll be easier to solve the equation. And also the Laplace transform that will convert the certain types of the initial value problems to algebra problems. If it is algebra problems, then it is easy to solve. So for both cases, you can see the main goal is to solve that easily. Let's do here. I can solve that easily or easy to solve. Oh, and also we can mark down that this is algebra problem. All right. Which means that the initial value problems, we transform that to the algebra problem. And for these algebra problems, we can find the solution of the algebra problem. And later on, you use the inverse Laplace transform back to the solution of the initial value problems. Okay, so we convert to another form, and then we will convert it back, do the inverse, then we get the solution. So maybe first in this field, it's really hard to find the solution. Then we convert it to another field. From this field, then we get the solution easily. And to get this solution, then we convert it back to the original form. And then since here we have a solution, then we convert it back to our original field to get the solution. That is Laplace transform. Okay. For example, when we have an integral equations like this forcing term, while we have the differential equation equals this forcing term, it's hard to guess the solution or even find the particular solution in the form of the particular solution. In that case, using the Laplace transform is easier. This is the integral equation. Okay, so now let's see our Laplace transform. Here's the definition. What is the Laplace transform and what does it look like? We say the Laplace transform of the function f is here. We do the integration and this is from 0 to infinity. We times e to the minus st with this function and do the integration. And this integration will be convergent. Okay? And we normally write the Laplace transform as the capital F of S. Or, that's it. Another form. If I have another function, okay, k times f of t. This k you can think about the e to the s minus st. First, here it is called improper integral. This is improper integral. What is an improper integral? Let's just quickly review that. To integrate from 0 to infinity, that means actually I have an integration from 0 to b. And the function of s and t, f of t, dt. And then I take b to infinity. So we have a limit, b goes to infinity. If this limit exists, then this integral is convergent. If this limit doesn't exist, then the integral is divergent. So let's have, suppose this is equation star. Okay, if the limit in the star, this equation exists, then we call that the integral is convergent. And then if it is not exist, then we call that this integral is divergent. Okay. So now let's just see this example. To find the Laplace transform of e to the at. So Laplace transform of this function f, which is e to the at, the function becomes a function of s. That means I do the integration from 0 to infinity, e to the minus st. And the function here is e to the at dt. That is e to the a minus st. Okay, so this improper integral, we can take the limit. So actually, you can think here is the integration from 0 to k, e to the a minus st dt. And then k goes to infinity. Okay, let's do the integration. 1 over a minus s e to the a minus st. And then this t is from 0 to k. And again, we take the limit, k goes to infinity. This gives you limit k goes to infinity 1 over a minus s e to the a minus s times k minus 1. When k goes to infinity, right here, I have 1 over s minus a. Well, if s is greater than a. Okay, now we have first note. F equals e to the at. Then the Fourier transform is 1 over s minus a. S is greater than a. Second note, the Laplace transform is a linear operator. All right. So now, since it is a linear operator, let's see the linearity. I have two functions, or two Laplace transforms, f and g. And the alpha, beta are any numbers. Then if I want to find the Laplace transform of f, the linear combination of your function f and g, then alpha f plus beta g. This Laplace transform is alpha Laplace transform of f s plus the beta Laplace transform of g. For s is greater than a. That is Laplace transform alpha f plus beta g, which means we do the Laplace transform individually and sum them together, or do the linear combination. Okay, let's have a proof. So suppose the Laplace transform of f and Laplace transform of g exist or converge. So this one is the Laplace transform of g. They both converge. Then let's see the linear combination of the function f and g. So the Laplace transform of alpha f plus beta g of s that's e to the minus st alpha ft plus beta gt dt. Can take alpha outside, e to the minus st f of t. and also beta outside the integral, e to the minus st times g of t dt. Then the first is Laplace transform of f. And the second one is beta times Laplace transform of gt. So here we say that Laplace transform, if the improper integral exists, the limit of this one, or the improper integral exists, or the integral is convergent, then we have Laplace transform. If the integral is divergent, then we cannot have the Laplace transform. So not every function has a Laplace transform. So not every function f of t has a Laplace transform. If the integration doesn't exist, or no, doesn't converge, right? Let's just do this example. What is the Laplace transform of 1? A constant number. So the Laplace transform of 1 is e to the minus st times 1 dt. Okay, so improper integral, let's have integration from 0 to b, e to the minus st dt, and that b goes to infinity. Then you have minus e to the minus st divided by s. T is from 0 to b. Then you get minus e to the minus sb plus 1 divided by s. We get 1 over s. S is greater than 0. The next, let's evaluate the Laplace transform of t. Okay, so I only have t. That'll be e to the minus st times the function. The function is t. Okay, let's do this in proper integral step by step. Again, and in the future, we just skip that process. We take the b goes to infinity. And then you can do it by yourself. We have minus t e to the minus st divided by s. And t is from 0 to b. And then also one more term, 1 over s, integration by parts. So we have 1 over s Laplace transform of 1s, which is 1 over s, and we just learned that the Laplace transform of 1 is also 1 over s. So it's 1 over s squared. Next, the Laplace transform of e to the minus 3t. That is integration e to the minus st e to the minus 3t dt. If you e to the minus s plus 3 times t dt. And then you have e to the minus s plus 3 times t divided by s plus 3. The t is from 0 to infinity. That gives 1 over s plus 3. S is greater than minus 3. So now we just have these 3 examples to demonstrate how do we calculate the Laplace transform. And those 3 functions are continuous. What if this function is not continuous? It's called piecewise continuous function. Piecewise continuous means the function like they are continuous, but at some point it disconnect. So x, y, so this you can see at t1. This is t1. Here we have t2. So we have jump. Having jump. Discontinuities. At t1 and t2. This is a piecewise continuous function. Okay. Now let's talk about the converge theory. Remember, when we talk about the Laplace transform, we say that if the limit exists, then the integral is convergent. How do I know that this limit exists or not? Here we have converge theory. So I have 2 functions. If the absolute value of this h function is less than g function, and then g function converges, then of course h should be converges. So we can try to find a function g that the integration of g converges, and also the function times the e to the minus st is less than this function of g. So one way to find this g, how do we find this g? Suppose my function f, the absolute value of this function is less than a constant m times the exponential. Then if I times e to the minus st on both sides, so this should be less than or equal to the constant m times e to the b minus s times t. This is another equation we will use. So let's see this equation, this integration. M times e to the b minus s times t dt. We say this integral converges if s is greater than b. Then we can choose the function g is m times e to the b minus s times t. Then the integration 0 to infinity e to the minus st converges. If we can find the m and also b, those two numbers satisfying this double star equation, then this integration converges. We can find numbers m and b satisfying the double equation. Okay, that's the theory. If you don't understand that much, that's totally fine. Let's see this example. If I have a function f, which is t squared, I want to know if the integration of f converges or not. In this case, if I can find the m and also b that satisfy this condition, then f converges. So here we can choose m equals b equals 1, because this function is t squared, and that's less than or equal to m equals 1, b equals 1, so e to the t, and t is greater than 0. Okay, exponential t squared, I think probably this. So it goes faster. It goes faster, okay? Next is the existence. How do we know that we have the Laplace transform? So suppose f is piecewise continuous, and we also have m and b that satisfy that, okay, f converges. Then in that case, Laplace transform exists. This is the sufficient condition, okay, not necessary condition. If f is greater than that term m times exponential, it may or may not exist Laplace transform. We just don't know. But the last one is more important. Okay, we may use that. We will use that later. For the Laplace transform, as goes to infinity, this limit will be 0. Okay, we will see that later. So here are two practice. You can try to find the Laplace transform. Okay. In the beginning, we said that why do we need a Laplace transform? We try to convert it to an easier way to find a solution. But once we find a solution, we need to retransform again back to our original field. So that's the inverse Laplace transform to show our answer. Just remember that on Wednesday, we talked about the Euler differential equation. Okay, we have the change of variables, change the equation to the constant coefficient linear differential equation. And then once we got the solution, we also need to convert it back to express our solution in x rather than in t. So here, this is the inverse Laplace transform. Since we know that e to the at Laplace transform is 1 over s minus a, then the inverse of 1 over s minus a, inverse Laplace transform of 1 over s minus a will be e to the at. Okay. And we also have a linear operator. If we have a linear combination of your Laplace transform, then the inverse Laplace transform for that, we can separate that. Okay, do the inverse Laplace transform itself times the constant, and then add them together. And we can also use the table to find the inverse Laplace transform. In our quiz and also the midterms, we will provide the table. So you don't really need to memorize a lot of transformation, a lot of form of Laplace transform. But at least the basic definition that you should know. Okay. That can also help you to verify your answer. So, for example, this, then I need to show the table later. All right. Find the inverse Laplace transform. This one, we can rearrange it because later on, if you see the table, try to find the same form or same pattern. Minus 2s divided by s squared plus 4t. And the second term, okay. And I will show you the table in class. And we rearrange that because we try to find the same pattern. If you check the table, you can see this pattern. This is cosine and this is sine. And that's why we have minus 2. Oh, here I have minus 2 cosine 2t. and then plus sine 3 times sine 2t. Okay. The other one is the partial fractions. Okay, so what is the partial fractions? Let's just review this. So for this S domain, I can express this fraction into simple form. Here I have s minus 1 and s minus 2 and s minus 4, s plus 4. Factor decomposition. Then I have a, coefficient b, the constant c. Okay. So we will compare the numerator. Okay, the left-hand side is s squared plus 6s plus 9. The right-hand side, it should be a times s minus 2, s plus 4, and b s minus 1, s plus 4. Last one is c, s minus 1, s minus 2. When you compare the s squared and the s and the constant term, you will get a is minus 16 over 5, b is 25 over 6, c is 1 over 30. Then your inverse Laplace transform of your a divided by s minus 1, here b divided by s minus 2, and c divided by s plus 4. So this is b, and here is c. This will be minus 16 over 5 times the inverse Laplace transform of 1 over s minus 1. Second term, 25 over 6 times the inverse Laplace transform of 1 over s minus 2. And the third term, inverse Laplace transform of 1 over s plus 4. Then you get minus 16 over 5. This is e to the t. Second one, e to the 2t. Third one, e to the minus 4t. Okay. Next, we're going to talk about the transform of derivatives, because we know that we want to find the solution of the differential equation. So we may have y prom or y double prom. And since we use a Laplace transform, then we really want to know what is the Fourier transform of the first derivative and also the second derivative. And I have already uploaded the table on the NTU core. As you can see this table. Okay, the second part, you can see that's why that from the last lecture, you can see the format, okay, to to see the inverse Laplace transform. If you have the Laplace transform in this form, like 1 over s minus a constant, then your original equation or function should be e to the at, the exponentials. Okay, so you can check that from the table. In the quiz and also the midterms, I will provide this table, just this page, okay? So now let's see. First, we want to find the derivative of the transform of a first derivative of the function. So again, since this is still a function, so think about this as a function. By the definition of the Laplace transform, we have e to the minus st times f prime. And then this is the improper integral, so we take the limit. The integration from 0 to k, and k goes to infinity. In this case, you will get, we need first integration by parts. Okay, because we have the t here and also t, another t. So what is the integration by parts? Here. Integration by parts. So that is u dv equals the function uv minus the integration v du. And apply this concept to this integration, we have limit k goes to infinity. Okay. U dv, you can think about this is u dv equals uv times integration v du. So uv, there will be e to the minus st times the function of f. That's e to the minus st f of t. And here k is from 0 to t is from 0 to k. Minus v du integration v du. Oh, we also need a limit. K goes to infinity. Integration 0 to k, and v du. V is f of t, and du d e to the minus st. Chain rule, we have minus s times e to the minus st. Okay? So here we have minus s times e to the minus st f of t dt. Alright, so the first term, k, t from 0 to k, and k goes to infinity, then we have k goes to infinity. Here t is from 0 to k, so e to the minus sk f of k minus when t is 0. When t is 0, e to the 0 is 1. Then we have f of 0 plus, okay, minus minus, we have plus s. We put s outside because s is irrelevant of your k. So it is irrelevant of k, then we put limit k goes to infinity. Here 0 to k e to the minus st f of t dt. First, what is this part? That is just Laplace transform f of s. Okay. So finally, you have s of f at 0 minus the function f at 0. Okay, because when k goes to infinity, this is 0. So we keep that term. Next, let's see the Laplace transform of f double prime. By the definition, yes, we have e to the minus st times the function. The function is f double prime. And again, that using the integration by parts, we have e to the minus st f prime. This f prime is your v. Okay. And then v du. So your v du, so you get s outside. Okay, same thing. Then you have minus f prime at 0 plus s Laplace transform f prime. This is Laplace transform of f prime, right? And then bring this here. We have s times s f at 0 in Laplace domain minus f of 0 minus f prime at 0. You can also continue to do this same thing to find the Laplace transform of f triple prime or even more, and you will see the pattern. Here is the pattern. Okay, suppose f prime, or you take the nth order n minus 1 order derivatives. They are continuous, and f n prime is piecewise continuous. Then, and also suppose that the limit is 0. When k goes to 0, you have e to the minus sk times the derivatives, jth derivatives, and at the k, then it is 0. Then your Laplace transform of your derivatives is the s to the n times the f at s and so on. Okay, this is the formula. But you don't have to remember this actually, because for our course, I think you only need to know y prime and y double prime. What is the Laplace transform of y prime and y double prime? Okay. So that means at least you should know Laplace transform of the first derivative, Laplace transform of the second derivative. Okay. So for example, if I have this form and I have initial value, so initial condition, okay. This is constant. You can also use what we have already learned, that the constant coefficient differential equation to find that. But we can also use Laplace transform to find the solution. Oops. Let's see the Laplace transform. So Laplace transform of y prime, there'll be s times the Laplace transform y at s minus the original function y at 0. Okay, then take the Laplace transform for this whole differential equation. We have Laplace transform y prime minus 4 times Laplace transform y, maybe y prime t, yt equals Laplace transform of 1. First, what is Laplace transform of 1? Check the table. It will be 1 over s. Okay, so here I have a s y of s minus y of 0 is 1 minus 4 y over s. That's 1 over s. Therefore, in Laplace transform, the Laplace field, you have 1 divided by s times s minus 4 plus 1 divided by s minus 4. Okay, and then again, find table. 1 over s minus a. Then the original function is e to the at. Okay. So here, y of t equals 5 over 4 e to the 4t minus 1/4. So in this case, we learned that using the Laplace transform, you see, I don't need to find the constant using the initial condition at the end. Do not find the general solution and then use the initial condition to solve the constants. Because when I apply the Laplace transform, we did it right away. Okay, because we need to use the initial condition here. Okay, let's do next one. We have a second order differential equation. For the second order, again, Laplace transform of y double prime, second term 4 times Laplace transform of y prime plus 3 times Laplace transform of y. That's equal to Laplace transform of e to the t. First, what is Laplace transform of y double prime? That's s squared y of s minus s times the original y at 0 minus y prime at 0. That gives you s squared y of s minus 2. And then Laplace transform of y prime will be s y of s minus y of at 0. Y at 0 is 0, so you only get s times y of s. So let's simplify that. We have s squared y of s minus 2 plus 4s y of s plus 3 times y of s. That's right hand side e to the t, 1 divided by s minus 1. See this table again. So here, e to the at, the Laplace transform is 1 over s minus a. That's why a is 1, s minus 1. Okay. And then your ys is 2s minus 1, s minus 1 times s squared plus 4s plus 3. So here, fractional decomposition, we have s minus 1, s plus 1, and s plus 3. Here we have the coefficient a and b and c. Okay, you can compare the coefficients in the numerator. Then you will get a is 1/8, b is 3/4, and c is -7/8. So you get 1/8, 1 divided by s minus 1. Second, b 3/4 times 1/s plus 1. And your c -7/8 times 1/s plus 3. Then your yt, that is the inverse Laplace transform. Will be 1/8. First, we know that this is e to the t. Okay, e to the t. Second, your a is -1, so we have e to the minus t. And then third, s plus 3, so a is 3, e to the minus 3t. Again, then you can check the table. You will use this a lot. Well, almost everything here I provide a lot, okay? So make sure that you do at least those 4 practice, okay? So the next we are going to learn is the shifting theory. Okay, what is the shifting theory? If I have a function f and that times e to the at, actually when I take the Laplace transform in S domain, they will shift. Okay, if it times the exponential, or well, if you times the exponential in other domain, they will shift by a. Next semester we will talk about the Fourier transform, and this is called the modulation. Okay, so if you times cosine or sine or even the exponential, then in other domain they just shift, and we will use that a lot, especially when dealing the signals, because you can let your signals in different frequencies, and then you can manipulate these signals, and then later on you take the inverse Fourier transform, inverse Laplace transform back to your baseband. We will talk about that later, but this is the shifting theory. And let's see the proof. Why the function times exponential, then in other domain, the Laplace domain, we have a shift. Because just based on the definition of the Laplace transform, e to the at the definition, the integration from 0 to infinity, e to the minus st, or and then my function e to the at f of t. And let's combine here. Combine the exponential term, e to the minus s minus a t f of t dt. And this is f s minus a if s minus a is greater than b, which means if s is greater than a plus b, the sum of a and b think about this is like a s prom. Okay, so here's s prom. Remember the Laplace transform e to the minus st f of t dt, that is f of s. Okay, now your s becomes s minus a. So s becomes s minus a. Okay, so suppose your function fs is here. First, this is your f of s. And if you shift by a, this is s equals a, and your a is greater than 0. This red curve is a shift of your blue curve by a unit. Okay, so if in your time domain you times the e to the minus st, then you will shift by a unit in s domain. Which means if we know the Laplace transform of your cosine function is here, s divided by s squared plus b squared, then you times e to the at. Actually, you don't have to do the integration. Okay, if you do the integration, well, you will see that I have exponential and also cosine. You need to do the integration by parts twice, but it is not necessary. Okay, you don't have to do that since you know the shifting theory. Here, if you times e to the at, your s will shift by a. That means your s becomes s minus a. So your s becomes s minus a. And here s minus a squared plus b squared. Okay. Now, next one. If we know the inverse Laplace transform f of s is f of t, then what is the inverse Laplace transform of your fs? But now I shift by a. So the inverse Laplace transform of your f, now your s shift by a. Then you in your time back to your time domain, we get e to the at of your times your f of t, the function f. Okay, it's just like a dual, one other dual. If you have a Laplace transform of the exponential times your function, then you have a shift. Then if you take the inverse Laplace transform, then that will go back to the f times your exponential. Okay. Next one, I want to find the inverse Laplace transform of this fraction. Okay. First, we need to check. Any form that we have we have s squared in the denominator. Okay, so those might be the candidates. Okay, so let's rearrange that. This is the inverse Laplace transform. That's 4 divided by s plus 2 square plus 16. You can think about this is the s square, okay? So if we have s square plus 16 in the denominator, we have this, right? S squared plus k squared equals k. Well, the numerator is k. So in this case, we can think about the original Fourier transform is 4 divided by s squared plus 4 squared. And then now I shift by 2. This one by 2 to the left. So that is the inverse Laplace transform. Of your fs plus 2. Then you get e to the minus 2t sine 4t. Okay, this one is sine 4t. Okay. Or if you check the table, you see that we also have this form. Okay, so s minus a squared, and you have the same b, then you know, okay, that's e to the at times sine. Okay. Any questions for this shifting theory and also this example? No? Then next one, we need to learn what is the Heaviside function, or sometimes you will see this is called the unit step function. Here is the definition of the Heaviside function. When t is less than 0, nothing. But once the t is greater than or equal to 0, then it is always 1. If I plot this function, it looks like so 0, well, here is 0 and 1. So when t is less than 0, nothing. When t is when t is greater than 1, okay. And the next one is a shifted Heaviside function. I shift till a. So sometimes I don't want to get 1 when t is greater than or equal to 0. I want to turn on the signal or turn on the light at a unit delay. So only when t is greater than or equal to a, then I turn on the signal. Then this is called shifted Heaviside function. Therefore, here is 1 and here is a. So before a, it is 0. Before a is 0. After a, it's 1. Alright, so here's a note that for this shift is that they will turn the function off until time a. and then they will activate it. Just what I said, that we will turn on the radio or turn on the light until until 8 units of time. Okay. So if I have a function as y equals x squared or t squared, then originally the function looks like here, y of t and t. This is y equals t squared. If I have this function times the shifted Heaviside function, which means t minus, suppose t minus 4, how does this figure look like? Here's t and y. Then suppose at 4, I want y equals t squared times this shifted Heaviside function. So we know here until 4, they were still off until 4, and they have a value 1. So until 4, before 4, there will be O0. Until t equals 4, then I have 1 times this function y. Okay, that's t squared. So that means here's O0, and then I have a value, and this value is 1. So I have a t squared. So I have a t squared, there'll be okay. Next, we will learn what is pulse function. So we can use the Heaviside function to create pulse function. So what is the pulse function? Only when t is between a and b, I have a value 1. Otherwise, there'll be O0. Okay, we can plot the figure based on this equation. Here's t, and this is h, and here's 1, and a and b. Okay, when t is less than a, 0, greater than or equal to b, 0, but between a and b, I have a 1. So you see, this is like a pulse. And because what is t minus a? This shifted Heaviside function. This is a, O0 until a, I have a 1. And how about t minus b? Suppose b is greater than a. Then here's the b. I have O0s until t is greater than b. So when I do the subtraction, so they will also cancel out this 1. So that's why we have 0 and we have a value 1 between a and b. Okay. So here is O0 until t equals a. And we have a value 1 till b. Then let's check if I still have t squared, this function y times the Heaviside function. The figure looks like this. But y times the pulse function, if I times y, then it looks like here's still A and B. It'll be O0, and after B there will be also O0. And then between A and B I have a value. This y is t squared times the pulse function. Okay. Now, if you don't have any questions, then let me ask. Then what is this function y of t minus a times this shifted Heaviside function? We learned that this is y times t squared times Heaviside function, shifted Heaviside function. Now, if my y is also shifted times a shifted Heaviside function, what does it look like? You can try to plot. Okay, you can draw your answer on the screen. So what does it look like? Based on those information, if y is still t squared, then y of t minus a times this shifted Heaviside function. I'll give you 1 minute. Then you can draw the answer here. Okay, I give you t, and here's y. And since they mentioned about a, so let's have an a here. Okay, let's go. If my y is t squared, then what is y of t minus a times the Heaviside function, a shifted Heaviside function? Show your answer on the screen. Okay, so I think most of the teams did a good job. Here I have 0 until a, right? So everything is 0 until a. And also I shift y by a. So this here I shift by a here. So I will get this part. All right. Next, I want to express the function of f of t as in terms of the Heaviside function. First, we can draw this figure. This plot, well, I have here's t, here's f of t. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Okay, so please help me complete the plot for this function f. Okay, again, then you need to draw your answer on this on the screen. Okay, so f of t is this. How do I express this function using this plot? The first one is easy. When t is less than 2, is 0. So I give you the start. Okay, so it's 0 until 2. And then complete the rest. Right, any thoughts? How do you plot this? When t is greater than or equal to 4, that's minus 4, right? So it should be here. And for this part, t minus 1, when t is 2, 2 minus 1, that's 1. So here. When t is 4, t minus 1 is 3, here. Okay. Now we need to analyze that. How do I use the Heaviside function to express this function f of t? So we will see that everything is 0 until time 2. Then I turn on t minus 1. And then I turn off this t minus 1 when t is when at time 4. So turn it off at time 4. And then I have value minus 4. So I turn on minus 4 at time 4. So for this two, I turn on and then turn off. That's h t minus 2 minus h t minus 4. And this one, turn on at time 4. That'll be h t minus 4. So the function can be expressed as t minus 1 times the pulse function minus 4 times the shifted Heaviside function. Okay.